Alright, so this is a Unit 11 nuclear quiz review that we have tomorrow, whatever, get it over with. Which symbol represents a nuclear emission? You want to look at your table O of your reference table, which you'll see right about here. Oh, well, we'll pass it, but you know. You're going to look at this list. That's going to be your particles you're going to select, whatever. It says greatest mass, that's going to be your alpha particle. I wasn't really here for this, but you know, it's a thought that counts kind of thing, right? But yeah, greatest mass, pick alpha particle. Number two, which emission will be released from an unstable iron 53 nucleus? You want to go to table N, right here. Look for F53F, which should be there, right there. It will be a beta, not a beta plus. It would be a positron, and you can tell that from right here, right there. And for the next one, let's see. Which particle has the least mass? That would be a beta particle. Beta particles are fast spinning electrons. Electrons are the most lightest particle in an atom, right? This is Unit 1 stuff. Just think of it, beta particle as, you know, a neutron. Not a neutron, an electron, my bad. This one, question 4. So this one you're gonna actually have to do some math for it. So what I did first and foremost was I went into the reference table for iron 53, right? We just looked at that for one of the earlier questions right there, 8:51 minutes, right? And if we go back to the actual question, this is, well, I can't highlight it, but right over here, 25.53 minutes. I'm gonna divide that by the 8:51. That should give me 3 half-lives, right? So what I did was take the 5.6, divided by 2. Well, you know, divided by 2. So 5.6 divided by 2, 2.8. Divide that, 1.4. Divide that again, 0.7. That's where you get your answer. And question 5. So what I found to help me the most was using fractions, right? So you want to set up your stuff like this, right? So before you even start with your half-lives, right, you start off with 1. Let me change that to a different color. So you start off with 1, right? Divide that by 2. That should bring you 1 half, 1 half, 1/4, 1/8, right? So on and so forth, 1/16, 1/32, right? So I want to draw a line here. That's going to be your first half-life, second, third, fourth, fifth. Ignore your number 1, right? That should be essentially what you should be thinking about in your head. For me, I would write this down on the actual, you know, quiz, test, whatever, to help you out so you don't have to refer to it in your head, right? But that should help you. So now in regards to the question, 2.5 years, what is a fraction of the original mass? Unchanged after 10 years. Divide 10 by 2.5, right? That should give you 4, right? So now you want to refer to the chart you made. Well, not really a chart, but the fractions, right? Which is right here. So you had 4, right? 10 divided by 2.5. That should give you 4. So you want to go 1, 2, 3, 4. 1/16th, right? So when it says which fraction of the original mass remains unchanged, you want to ignore the unchanged. Just look at it like this. You got an isotope has a half-life of 2.5. What would be the half-life in 10 years, right? Don't quote me on that, but you know, that's an easier way to understand it. Because that's what I was confused on originally for the homework, right? But for question 6, after decaying for 48 hours, a 16th of the original mass remains unchanged. Same thing. So if we go back to the chart, right? which is right here. A 16th of the original mass. So that's after 4 half-lives, right? So you want to go back to the actual problem. Divide 48 by, well, 4. It should give you 12 hours. That's your half-life right there. Number 7. This is essentially what you did for the first question, albeit a slight change. Right, so beta particle, yeah, less mass. It's small, so obviously less mass, but it's able to go through stuff way easier, right? So if you think about like the gaseous scene, like atoms, molecules, whatever. If it's small, it can go through easily. If it's bigger, like an alpha particle, not as easy, right? That's that for number 7. Number 8, this is a natural decay, right? As you can see right here, occurs naturally, but it's scarce, whatever. Here you want to pay attention. So make sure there's only one thing and an arrow for a natural decay. And what you want to make sure to know is make sure the atomic charges line up, first and foremost. So 82, and then 2 right here, right? And then those line up, add up to 84, 206, 204, 206 and 4, that makes 210. There you go. Make sure that lines up. Essentially just make sure all the numbers add up to 210, 84, right? That's that. Question 9, same concepts. You don't need to look up for the reference table or anything because they give you the actual decay particle. Make sure it adds up. 55 minus 1. Well, actually, what minus 1 equals 55? So add the 1 instead. 56. Another thing, make sure the atomic masses line up. 137, there's 0. So 137 should be right there for the mass. And stability, for this one, odd numbers don't really matter. So for my note for myself, I wrote, you want to pay attention to the mass numbers, right? So if you go into your reference table, or for example, what I use is oxygen, right? You want to make sure they're equal to each other, right? So 8 plus 8, 16. But obviously your protons aren't going to change, or else it will become a different element, right? So your neutrons change, right? So you see 3 more neutrons, thus making it unstable. More neutrons than protons. There's your answer. Nuclear fusion, we all know this. Matter is converted to energy. Simple stuff. Ionic covalent bonds, that doesn't matter. It's reverse for energy is converted to matter. Alright. Undergoes transmutation reaction, it emits whatever particle, right? Reference table for this one too. Alright. So right here, 226 Ra. There's your alpha particle indicator thing. Alright. That's that. So next question. 13, natural nuclear decay. 1 reactant, obviously. And make sure atomic numbers line up, atomic masses line up. Same thing, right? And actually for this one, make sure there's actually a nuclear decay particle, right? So for that you want to look up here, make sure at least one of these notations are in the problem. If not, then you know that's not natural, or actually a nuclear decay at all. But yeah, in fusion, most of the time you're gonna see a hydrogen problem, or hydrogen equation bad. So 2 hydrogens make He, right? These 2 add up like that. These 2 adds up to that. Most of the time you're always gonna see a hydrogen, right? Energy is released. So that's pretty much it. Hope that helps.